But we're measuring this. And what happens if we do also a virtual zero reference? We add our own virtual zero reference. We estimate what B is. And do minus here. What would this do? What would this do? I need to give it a different color. This is controls, not physical system. These two would cancel, right? So I have the same gain, the same thing going on, but here it's minus, here it's plus. And these are essentially the same. So whatever this value is, this is the same value, and they cancel one another. We call this decoupling state feedback. It basically makes this gain almost zero, depending on your parameter estimation. I put a hat on top of this because we never know our parameter is perfect. But we'll see what this does. But essentially, we steal the gain from our zero reference and our system doesn't go back to zero. So we have no controls in there yet. But if you were to implement this on any system, it wouldn't look like friction at all. So you put your pan on the board, on the ground, and you push it once and it would just keep moving. It would never stop. Because that's naturally what decoupling state feedback does. And if you think about controlling something where it's not speed dependent anymore, how much friction or how much force you need, that's probably a good idea, right? Controls would be easier if it's not depending on the speed anymore, how much force you need to move it. So it can be a really good idea to do this. And now let's see what this also does for us. So now let's say, okay, we decoupled this and now we want to do an actual control. So we use, I should use also a different color. This is still the measured speed. And now we give an actual reference, right? This is our actual reference to our system. We give it a gain, let's call it an active BA. And put this on top. So this is like a P controller, right? You have a gain, and then your whole system comes. And this is almost decoupled. But we'll see what this now does. So if we now look at command tracking of this. And that's not already clear. Command tracking is basically the transfer function between our state and our reference. So look at V of S over V star of S. And I'll shorten the algebra real quick. You can do this at home. But this will turn out to be BA over M times S plus BA plus B minus B hat. And if we now look at V of S, or over V of star of S, at steady state, which means frequency is 0, this becomes BA over BA plus B minus B hat, right? And what does this tell us? What did we change here? We actually have a P control here that has almost no offset error. If B hat is correct, this is 0 and this is a perfect one, right? And people will always keep, or everyone, but people might tell you if you have a state feedback like this, you will have a DC offset or a steady state offset error, and you use an integration to get rid of it. I'm saying that's not the only way, and I'm saying you probably want your integration to not be built around this, probably around disturbances. And this already gets rid of offset errors anyways. Okay, so now you might be saying, Mike, but what if you don't know your parameter correctly? Okay, well, let's do an example. Let's say, and your BA, whatever system you have, is very, very probably will be way bigger than your B. But again, you might have an issue. Let's use an example number. This might be even over-exaggerated. Let's say BA is a value of 10, and B will be a 1. Let's say you have a 10% error in our estimation. Then our B hat might be 0.9. Okay? So just a numbers example. And what will this wind up be? This will be 10 over 10.1, which is 0.99. So it is not a 1, but you have a 1% error in your steady state, which is probably more accurate than your sensors anyways. So you will not see this as an offset error. You will see 10% of an offset error, but not 1%. And you get rid of this by this really easy trick. And if you really think about this, this makes a lot of sense. If you don't have this decoupling, then there's two different references on your system. One has this gain, and the other one has this gain. You can basically think about this as you have your mom on your one side and tell you to bring out the trash. And then it's your father on the other side who tells you to help him in the garden. And both are yelling at you. And they have, if these gains are basically the same, then you might be, you don't know what to do, right? You're exactly in the middle. And that's your DC offset error, because they both try to get you somewhere. One to 0 and one to your reference, so you wind up somewhere in the middle. But if you increase this, you give one a megaphone. Your mom has a megaphone now, so you naturally draw closer to her. And if you make this super, super big, your DC offset error also becomes small. But she also has a megaphone and screaming. That might be a problem, also control-wise. But this here, what is this? This is basically cutting off your debt. You don't hear her anymore. And your mom does not have to scream. Right? She can speak normally and you still only hear her. So that's another approach to do this. You don't have to have a megaphone, you can also just decouple his voice and clearly hear your mother's voice. It actually makes a lot of sense control-wise because this also introduces voice. Okay? And you will see this in the homework 1. We only use a P control and only state feedback decoupling, and you will see you don't necessarily get DC offset errors. Or steady state offset errors. Okay, anyways, so this is now our command checking. And surely now, with the same approach as in our dynamic stiffness, we can also plot this. And usually for command tracking, we want two things. Also for dynamic stiffness, actually, it helps to also look at not just the magnitude, but also the phase. So here's also the phase, and this would be the magnitude. I will talk more about these plots in the next lecture. However, we can do this rather simple, right? So at low frequencies, what dominates here? What dominates up here? There's only one thing, right? So this dominates. What dominates down here at low frequencies? BA, right? If S is really, really small, then this is gone and you only have BA. And obviously this. This is also the case. If this is nearly 0, then we have, again, our 0.99, or basically a 1. So in low frequencies, you will get this behavior. If F is now going up, this will, so here it's basically BA over BA. So pretty close to 1. Again, if you don't decouple it, it's a little bit smaller, so then it's VA over VA plus B, so not perfectly one. And at higher frequencies, this will be VA over M times 2 pi F, correct? Or M times J 2 pi F. To also look at the phase. So this definitely has a phase of 0, right? There's no J involved, so no phase, and also a 1 in magnitude. Here, it will go down with frequency, so we know that it will do this. And this, at really, really high frequencies, is say 1 over J, right? So it's minus J, so minus 90 degrees, correct? So it will start at 0. At the break frequency, actually, it's right in the middle, right between no angle and 90-degree angle, so it's minus 45. And in the end, it will reach minus 90. Right? So very simple. And again, here we again have the same thing. We have a break frequency. And we can also calculate this break frequency. Where does it happen? Where is F break 1? It happens when this stops dominating and this starts dominating, right? Or when they both are equal. So it happens when M times 2 times pi times our break frequency equals BA. This is already your calculation for your controller. You can choose the break frequency of your controller. This also this upper break frequency, because everything up to 1, that's what our controller is supposed to do. After that, it's not doing what it's supposed to do. That's also why people call this point your bandwidth. Up until that point, we track. It already has an issue, right? So you already have 45 degrees error, and this magnitude looks okay in a Bode plot and logarithmic, but it is also has some magnitude issues at that point also. But that's what we call the bandwidth. And it's really easy to set this bandwidth. It continues to remain very, very easy to calculate this. These really easy approaches. Does this make sense, or?
Yeah, how about if we have a 0 there?
A 0 where? Oh, if we have a 0 up here?
Yeah. Like for example, we have 1 0 there.
But where does it come from? So if there was a 0, if you have like this,
yeah,
then obviously this would be at low frequencies going up, and then infinitely, or then this, if you make this M for instance, I mean that depends on what you do, but if you make this M, then it would be an infinite one, and below it would look like this. It's like a high pass.
And then we have calculated break frequency that follows the same.
Yeah, but you only track above this, so that's a high pass filter. But it's not really control. If you want to control the high stuff, yes. Then you do a high pass filter control. Sometimes people put this on their state feedbacks. With the state feedback control, they might put some filters on it to only control something up there, or have an active state feedback only at high frequencies or at specific frequencies. Then you can also put filters on your signals. But they always introduce also phase issues. Okay, so this, I want to redraw this here a little bit. Still the same system. I'll just draw it more in the control format. This is V of t. say we have a V star. And we have our VA here. So this is what we did, right? Now what happens, so this is a reference for our speed. What happens if we give more references? Let's say we also give a reference to our position. And we have a reference position. And we make a force out of this, so force and position, what's that physically? This here is like a physical friction, right? This is a physical spring constant that we have here. It creates force. So what would this do?
So we have multiple input.
Let's do the math together, what this does. And maybe you find out what I actually did there, and you basically, you might call this something else. Let's do the math. So, I want to see the, for instance, the command tracking here. We want to see this over this. So Vs over V star. And we do the normal algebraic way now to do it, not the Mason's rule. So V star is basically, this Vs is V star of this times, and if you think about this, what's the definition between these two here? X star of t should be the integration of speed, right? Where dx dt should be v of t, right?
Yeah.
So we also know that this, between this is an integration. They should make sense to one another. Always important, the references should make sense to one another, otherwise they're fighting each other. This way they're actually trying to do the same thing. So it actually winds up to look like this. VA, where we start, and then times our plant. Then we also have our state feedback minus E of S times K of S plus VA times 1 over MS. Right? So it's only this times this, and this is the X up here. And now if I just do the algebraic back and forth, you should see that we see something like this. Looks like Mason's rule, right? All we did is Mason's rule. Like this over 1 plus this, right? And it winds up to be K over S plus BA over M times S plus BA plus K over S. So pretty much looked like the one we had before, just the K over S came up here and here, right? Unfortunately, I erased the old one that we had, so I'll just do it one more time. So the one we drew before was this green one look like this. And let's do it now for this example here. So what happens at small frequencies, very small frequencies? What is the command tracking now?
K1 will be
What dominates up here?
K.
K over S, right?
Yeah.
And down here?
K over S.
Also, correct. So the whole thing becomes
1.
K over K, so 1. And this is actually a perfect one. There is no reference that kills this, right? So this will be a really, really perfect one. So then we get to the mid frequencies. What does this whole thing becomes? Up here,
1.
BA, right? Down here, also BA. So it's BA over BA. And technically, if we still have state feedback, it would be BA plus B minus B hat, or if we don't decouple it, plus B, but also pretty much 1. So it could be not perfect, but almost perfectly 1. Depending a little on the parameter estimation. If we don't decouple perfectly, it's not perfectly 1. And at really high frequencies,
B over M.
B over M times 2 pi f, right? Or J. Still S.
Yeah.
So it also goes down. This has no angle, this has no angle. Also again 1 over J. So in phase and magnitude, they don't really look all that different. Right? I mean, they pretty much do the same thing. If you decouple perfectly, it's pretty much the same. However, I tell you what the dynamic stiffness look like. Let's do dynamic stiffness for both of them. So for the first example, the green example, the dynamic stiffness is ms plus BA. For the black example, dynamic stiffness is m times s plus, plus BA plus K over S. So the green one here starts dominating, right? So it's just a BA and then F's dominates. So it looks like this. The black one though has this at low frequencies, right? We saw that before. It will look like this. So in command tracking, this really is